Hi guys, welcome to the video. This is a short one, hopefully, just a quick theorem from Fundamental Applied Maths. It's called Theorem 11.1 in the book. It's on circular motion again. And this is the idea that the acceleration of an object moving in a circle is towards the center of the circle and has magnitude omega squared r. So first of all, just a quick discussion of what we're talking about here. If an object is moving in a circle, the velocity will always be tangential. Okay, so there's a velocity vector. And the acceleration is towards the center. So the reason for that is because the velocity is changing as it comes around. This object, even as it's moving with a constant velocity, that is the velocity, the size of the velocity isn't changing. So constant speed perhaps, is what I should have said. The velocity is changing because as you turn, the direction changes. Okay, so if you have a change in direction, that's a change in velocity. Okay, that violates our a body in motion in a straight line will continue moving in a straight line unless an unbalanced external force acts, all that. So it's accelerating somehow, and this theorem says that it's accelerating towards the center. So that's pulled into the center is what causes the velocity to change as it goes around. In the absence of that pull to the center, this object will move in a straight line according to Newton's first law. So the acceleration is towards the center is what we're trying to show. I'm going to start off by saying this point up here on the circle is called xy. That's the position of the object moving in a circle. And that's labeled S. I should have labeled that R. Okay, S we are going to use for our position vector, so we'll see that in just a few minutes' time. This angle here, if it started at this point down here, okay, and it's moving with angular velocity omega. Okay, so that's how many degrees it rotates per second or how many radians it rotates per second. We're going to work in radians as we always will in this chapter. Well, if it's rotating at 0.2 radians per second, after 1 second it's here, after 2 seconds it's here, after 3 seconds 0.6 radians, after 4 seconds 0.8 radians, and after 5 seconds maybe you're up to 1 full radian. Okay, but the angle that it's going to subtend is its angular speed, say 0.2 radians per second, multiplied by the time that it's been rotating for. Okay, so omega t is the angle that it subtends there. So I'm just going to look at that right angle triangle down here in a little bit more detail. There's omega t, there's the radius, and the x coordinate is whatever this is. Okay, it's the adjacent side of the triangle, and the y coordinate up here is whatever this is, whatever the opposite side is. Okay, so we can say, well, I know that sine of omega t is the opposite side over the radius. Multiplying through by r, I get y equals r sine omega t. Same thing, cos of omega t is x over the radius, multiplying through by r cos omega t is the x coordinate. Okay, so that's r cos omega t and r sine omega t. So my position up here now, and I'm going to write it in I and j terms, my position vector, I'm going to use S for position, is r cos omega t in the I direction plus r sine omega t in the j direction. Okay, so that gives us a position on the circle. Okay, so that's working in circular coordinates really. What we're interested in is the acceleration, and hopefully we know from calculus that the rate of change of displacement gives us velocity, so we can work out the velocity here in a second by doing ds dt, the rate at which this thing changes with time. And once we know that, the acceleration will be dv dt, the rate of change of velocity. Another way of saying that is acceleration will be the second differential of this. So what's the first differential? Well, differentiate here, you're going to get r, differentiate cos, you get minus sine omega t, and then because you have a function within a function, the chain rule says multiply by the derivative of omega t, which is omega. So that's the I direction, plus r doesn't change, differentiate sine, you get cos omega t, and the chain rule says multiply by omega. Okay, and I'm running out of space, but that's in the j direction. So let's just tidy that up. We're saying the velocity is omega r minus r omega sine omega t in the I direction, plus r omega cos omega t in the j direction. So that's our velocity vector. Well, our acceleration vector then is dv dt, okay, the differential of this, or the derivative of this. So what's that going to be? It's going to be minus r omega, differentiate sine, you get cos omega t, and again by the chain rule we need to multiply by omega, the whole thing by omega. That's the I direction, plus r omega, differentiate cos, you get minus sine omega t, and again by the chain rule multiply by omega. That's in the j direction. So we're getting, for our acceleration, we're getting minus r omega squared cos omega t in the I direction, minus r omega squared, minus by r omega and by omega squared, sine omega t in the j direction. You've got a common factor of minus r omega squared. Actually, I'm going to leave the r in, and I'll tell you why in a second. So minus omega squared times r cos omega t I plus r sine omega t j. Well, that there is just our original displacement function. So our acceleration is minus omega squared times our displacement function. And because our displacement is from the center here going outwards, the acceleration is a negative vector. That means a vector going in the opposite direction. It's going inwards. So therefore, acceleration is towards the center. Furthermore, the size of that acceleration, the magnitude, is given by kind of doing a Pythagoras on this. So it's going to be the magnitude squared is going to be minus r omega squared cos omega t, cos all of that squared, plus minus r omega squared sine omega squared t, all of that squared. Sorry, that's not squared at all there. So squaring that out, we're going to get positive numbers in both cases. So we get r squared omega to the fourth cos squared omega t plus r squared omega to the fourth sine squared omega t. Taking r squared omega to the fourth out as a factor, r squared omega to the fourth times cos squared omega t plus sine squared omega t. Hopefully we know our identities, page 13 or 14 in the log tables, I believe. Sine squared plus cos squared together always equals 1. So this is r squared omega to the fourth times 1 if you like. So that tells us that the magnitude of a, that vector, is the square root of, that was a squared, so it's the square root of this, r squared omega to the fourth, which is r omega squared, which is what we were trying to show, omega squared r. Okay, so what we got out of this was two things. First of all, acceleration vector is minus omega squared times the displacement vector. We're going to use that from time to time. And secondly, the size of that acceleration vector is omega squared r. Okay, see you next time.